Good afternoon, guys. Welcome back. So we are getting ready to start lecture 6. I believe it's lecture 6, chemical reactions and equations. Sorry, since we moved things around, I'm not exactly sure which lecture number this is anymore, but I think it's 6. And like I said, chemical reactions and equations is what we're going to be talking about today. So I'm going to pull this over here. We may need our periodic table. I'm actually going to do this for now. So that's what we're going to be talking about. Chemical reactions, chemical equations. We're going to talk about balancing them. We'll do some practice with balancing chemical equations. We'll talk about nuclear reactions, their definition, the elementary particles that are required to talk about these, and then we'll practice balancing nuclear equations. So that's everything we're going to talk about here. That's the last topic that we're going to have before the first exam. Now we're going to have one more lecture before the first exam, but that is not something that's going to be covered on the first exam. It's just something that I typically talk about because I think that it helps to bring things together before the first exam, but it's not material that's going to be covered. Now, I want to do some review of stuff that we talked about from the last lecture. So for the following mass/composition combinations, we want to calculate the number of moles and the number of molecules. In 600 grams of NaCl, 462 grams of PbSO4, and 13.65 grams of Mg3PO42. We want to know what the percent composition of NaCl, PbSO4, and Mg3PO42 is. I want to know the empirical formula of a compound that's 69.94% Fe and 30.06% O. And what's the molecular formula of a compound that has a 75.46% C, 4.43% H, and 20.10% O by mass if the molecular weight is 318.31. So I'm going to go ahead and pause here. I'm going to stop recording for just a minute. And I'll be right back. Okay, so I need to grab my calculator. We're probably going to need that to be able to do this. Now, the first thing I want to do is to calculate some molecular weights. So I'm going to look at my periodic table so that I can do that. We're going to start with NaCl. So I see that my Na is 22.990. Cl is 35.45. I have Pb, S, and O. Pb is right here, 207.2. S is right here, 32.06. And O, again, 15.999. And we've got M, G, P, and O, which again, I have O, so I'm not going to write it again. But our Mg, 24.305. And phosphorus here, 30.974. And those are all in grams per. So that means that my sodium chloride is 22.990 plus 35.45, which gives me I don't want to move things. 58.44 grams per mole. Our PbSO4, 207.2 plus 32.06 plus 4 times the 15.999 gives me 303.256. And check, and my NaCl I'm going to leave as 58.44 because since my Cl only has 2 decimal places, I don't know it any more than that. My PV, this technically I should be rounding to this tenths of the decimal place because I only know my 207.2. So from a technical standpoint, this should be 303.3. So remember that it's only significant to 303.3. I'm going to work with the entire number when I calculate, but. And then our Mg3PO4, 24.305 times 3 plus 2 times phosphorus, so 30.074 plus 8 times 15.999. And I end up with 261.055. And because the least precisely known of those numbers, 3 decimal places there, 3 there, and 3 there, all of them have 3 decimal places. So this number has 3 decimal places. So I can keep that exactly as it is. Okay. Now, I have 600 grams of NaCl. I want to calculate the number of moles and the number of molecules. So if I wanted to calculate the number of moles, I'd take my 600 grams of NaCl, and I would divide by the molecular weight. So the molecular weight is 58.44 grams per 1 mole for NaCl. Okay, so I take 600 divided by the number that I calculated, at 58.44. And that ends up giving me 10.2669. Looking at this, I only have one significant figure in the 600. So I should report this as 10 something, but I can report it as 10 moles of NaCl. Because that's 1 sig fig. Okay. Now, that is how I would calculate the number of moles. Now, I'm going to calculate the rest of these on a separate piece of paper, so we'll talk about that. If I wanted to then calculate the number of molecules that I had, I would take my number of moles and I would multiply that. So I would multiply this by Avogadro's number. So 6.022 times 10 to the 23rd, and that's particles per mole. Particles per mole. So I can take the number that I just calculated before I rounded it, times 6.022 second EE23, and I end up with 6.18 and a bunch of decimal places times 10 to the 24th. But that's only significant to 1 sig fig. And again, that is based on the 600 that I started with. So 1 sig fig, I would report this as 6 times 10 to the 24th molecules. Okay. So based on my sig fig, 6 times 10 to the 24th molecules. Questions, comments, problems about that? All right. I'm going to, again, get another piece of paper. And then I'll look at how many grams, 462 grams of PbSO4. And I know that molecular weight for the PbSO4 that I calculated. Mistaken. Was 303.256. Which should have been reported to 0.3. So should have been, as far as sig figs go, 303.3 per sig figs. Now this is only 3 sig figs right here, so that's going to limit my number of sig figs anyway. So I'm not going to worry about paying attention to the number of sig figs on the molecular weight. This is grams per mole. And if I do that math, 462 times the number that I calculated, that not times, divided by the number that I calculated, that 303.256, that ends up giving me 1.52 moles of PbSO4. I can take that 1.52 moles of PbSO4, and of course, on my calculator, I'll keep the whole thing that I calculated, and multiply by 6.022 times 10 to the 23rd molecules per 1 mole. Moles cancel. Multiply that by 6.022 second EE23. And that gets me 9.17 times 10 to the 23rd molecules. And those are molecules of PbSO4. Now, is it required that I say molecules of PbSO4? Not really. Okay, I just need to know how many molecules there are. But for me, I feel more comfortable reporting them as molecules of PbSO4. Okay, that is something that I do. All right, so those are my answers for PbSO4. And the next thing it asked me about was 13.65 grams of Mg3PO42. So 13.65 grams of Mg3PO42. Molecular weight that I calculated here was 261.055. So 261.05 grams per 1 mole. So 13.65 divided by 261.055. And I get 0.052. I should have 4 sig figs, so I'm 0.05229 moles of Mg3, and it's not going to fit, so Mg3PO42. So that's how many moles of that material that I have. Going from moles, 0.05229 moles, 6.022 times 10 to the 23rd molecules in 1 mole. Moles cancel. So I multiply this lovely number that I calculated times 6.022 second EE23. And I end up with 3.14. And again, should be 4 sig figs based on this number that I have here. 149 times 10 to the 22nd. And I say that because I'm not limited by the number of sig figs that are here, and this is considered infinitely significant, so it should be based on the number of sig figs that I have in this number. So, and that is molecules of Mg3PO42. So those are the answers that I needed for that first question. Okay. Now I'm going to come back here. The percent composition of NaCl. Okay. Well, if I want to look for percent Na, I know that that's going to be based on the mass, that's Na. So 22.990 grams. Or the mass of the whole thing. So the mass of that NaCl we calculated to be 58.44. 58.44 times 100, right? So 22.990 divided by 58.44 times 100. What did my calculator hates me sometimes? 58.44 times 100. And I end up with 39 point. Again, should be 2 decimal places here, which ends up with 2 decimal places there. So 4 sig figs in that number, 4 sig figs in that number. So 39.34% NA. I'm going to get percent CL. It's going to be that 35.45 divided by the 58.44 grams. Both those are grams times 100. 35.45 divided by 58.44 times 100. And that gives me 60.66%. And if I were to add those together, I end up with 100%. So that makes sense to me. So that's my percentage of NA and percent CL within NaCl. Okay. Now, I'm going to go with PbSO4 over here. (207.2 grams divided by the total mass for PbSO4, which is 303.256. And again, this should be 303.3 based on the fact that this is 207.2. So 207.2 divide 303.256. Multiply that by 100. That gives me 68.33% for sig figs, because this number has 4 sig figs in it. Okay, so 68.33% S. I know that the molecular weight of that S, based on this, 32.06. Oops, sorry, went too far. 32.06. 32.06. By that 303.256. And this should be times 102. Apologize. So 32.06 divided by that 303.256 times 100 is 10.4 sig figs in this number, so 10.57%. And our percent O equals 15.999 over 303.256 times 100. Now this should only be 4 sig figs because it should have been rounded based on that. So I'm going to count this to 4 significant digits as well. 15.999 divided by 303.256. So I'm not rounding it as I calculate with it. Times 100. Reporting it as 5.276%. Looking at my percentages, adding them together. That ends up with being 84, and that doesn't make a lot of sense to me. Oh, that's because I didn't multiply this by 4. So I failed to take into account all of the mass that should come from the oxygen. So 15.999 times 4 should end up being 63.996 divided by 303.256. And then multiply that by 100. this should then be, instead of being 5, should then be 21.1% for sig figs there. And if I do that math, that should make a lot more sense. And that is equal to 100%. So, geez, make sure that we take everything into account and we should be fine. Okay? So those are my percent by mass. Now, what is the empirical formula of a compound that's 69.94% Fe and 30.06% O? Now remember, when we talk about our percent compositions, we're going to assume that our total mass is 100 grams. And that means that each percentage is the mass out of 100 grams that each thing has. So I have 69.94 grams of Fe, and I have 30.06 grams of oxygen. I can then convert that to moles by dividing by the molecular weight. So Fe, I haven't looked it up yet, so I gotta go find the mass of Fe. That's 55.845. in 1 mole. So 69.94 divided by 55.845, and that's 1.25239502 moles. 30.06, and divide that by 15.999 grams, 1 mole of oxygen. 30.06 divided 15.999, and that gives me 1.87886749. So if I were to set this up the way that we have been, that Fe 1.2523950222 and O 1.87886749. And I divide them both by the smaller number. So that 1.2523950222. Obviously, that gives me Fe, but I have to divide that oxygen by that 1.25, and that gives me 1.500. Now, there's a whole bunch of other stuff too, but I'm going to leave it as 1.50. I do that because I had 4 sig figs here, so I'm leaving it as 1.500. And because it's a 1.5, that's not an even number, so I'm going to multiply this whole thing by 2, which means I get Fe2O3. And that is the smallest whole number ratio, or the empirical formula for this compound, Fe2O3. And in my head, that actually makes a lot of sense because oxygen usually has a charge of -2. And I know that Fe can have a charge of +3. I've seen that before. So that makes sense to me. Okay. Now there's one more percent composition that we've got. And so I see that I have 75.46% C. It said I have 4.43% H. And I also have 20.10% O. And there was one other thing it told me, and that was the molecular weight is 318.31. Okay, I'm going to start just like I did before. Okay, so I assume that this percentage is a mass out of 100 grams. So 75.46 grams of carbon, 4.43 grams of hydrogen, and 20.10 grams of oxygen. Converting up all of those to moles, I need to know the molecular weight for carbon, which is 12.011. Hydrogen, here 1.008. Mole of hydrogen. And then looking at that oxygen, I've got 1 mole of oxygen is 15.9 grams of oxygen. So do a little math. 75.46 divided by 12.011 gives me 6.282574,307, and that's moles of carbon. 4.43 divided by 1.008 gives me 4.39484127 moles of hydrogen, and 20.10 divided by 15.999 gives me 1.25632851 moles of oxygen. So we always write this as a formula, right? So we have our carbon, and the number that went with that was 6.282574,307. I'm reading it from my calculator. We have our hydrogen, and that was 4.39484127, and then oxygen 1.25632851. Divide by the smallest number, which happens to be the oxygen, 1.25632851, 1.25632851, 1.25632851. So my oxygen is obviously going to be a 1. If I take that 6.28 and I divide that by the 1.256, I end up with carbon 5.000. 4 sig figs, because the number I started with the carbon was 4. And then my hydrogen, I take that 4.394, I divide that by the 1.256, and I end up with a 3.498. And again, I should only have 3 sig figs. I wrote down 4. Again, I have 5 here, I have 3.5 here, and I have a 1 there. 3.5 doesn't work, so I'm going to multiply everything by 2. And that's going to give me a C7 H 3.5 times 2. That's not C7, that's C10. 10 H7O2. So that looks like the empirical formula that I have for this compound. Now, I want to know what the empirical formula mass is. So I have carbon, which is 12.011 times 10. (120.11). I have hydrogen, which is 1.008 times 7. 7.056. And then oxygen, which is 15.999 times 2. which is 31.98. And if I add all of those together, I end up with 159.164. That is not consistent with the molecular weight that I was given. The molecular weight that I was given was 318.31. So I can take that 318.31 and divide it by the number that I just calculated. So 318.31 grams per mole divided by 159.164 grams per mole is equal to 1.987, which is approximately 2. So if that's true, then I would need to multiply this whole formula by 2. So if I need to multiply this whole formula by 2, then my molecular formula is going to be C20H14O4. Because again, C10 times 2, C20. H7 times 2 is H14, and O2 times 2 is O4. And if I calculate that molecular weight, so 12.011 times 20 plus 1.008 1.008 times 14 plus 15.999 times 4. And I end up with 318.3 when I calculate. Okay, so that's consistent with what I was given. Does that make sense? So I know that my empirical formula was not enough to get me to the mass that I needed. So the mass here being 159.164 wasn't enough to get me to the 318.31. I needed to multiply by 2. That got me to C20H14O4, and that mass was 318.3. Okay, so that was consistent with the mass that I'm supposed to calculate. Okay, so that is our review of the things that I was doing the last time. Okay, so hopefully you're good with that. But if you're not good with that, let's talk about why we're not good with that. I want you to be comfortable with these things. We should be okay with that now. So things that I'm expecting is that you can calculate the number of moles based on a formula and a molecular weight. You should be comfortable writing a formula at this point. So if I hadn't given you a formula and I said sodium chloride, or I said lead sulfate, or I said magnesium phosphate, you should be able to write those formulas and then calculate a molecular weight. Okay, you should be able to calculate the number of molecules if you're given a weight of a material or the number of moles of a material. You should also be able to go backwards. So if I tell you how many molecules you have, you should be able to tell me how many moles you have. If I tell you how many molecules you have, you should be able to tell me what the mass of that sample is. Okay. You should be able to calculate a percent composition for any given formula. You should be able to use an empirical to find an empirical formula based on a percent composition. Okay. You should be able to use information about percent composition to find a molecular formula if you know information about the molecular weight. Okay. So you should be able to find the empirical formula and see if that matches the molecular weight that you're given. All right? Questions, comments, problems on any of that? Okay, we're going to take a break here. I'm going to stop the recording at this point. We'll come back to chemical reactions and chemical equations in just a bit. I'll see you soon.